So welcome to my talk. I'm Nicolas Lopez, and today we are going to talk about Assassin's Creed Shadows. So today is also the launch date of the game, and you have no idea what it means for me to be here for this special day. We made it. Thank you. So I won't ask you who has played the game. I guess nobody yet. But I want to take a minute to thank the whole Anvil rendering team. They've been awesome, and we made a ton of tech, and a lot of it is missing in this talk because it would have been a day long. I also want to thank the Assassin's Creed Shadows production team, and everything discussed today is really a team effort. So first, if you want to find me online, this is probably the photo you want to take with Twitter, Blue Sky, and Mastodon tags. And these are some of the games I worked on. And now I will show a trailer of the game to give a bit of context to this talk.
How can we build a land of peace on the backs of 1,000 dead?
You'll have to kill them all. Do you understand?
Fight for what is right. For the freedom to seek justice.
Together, we will be unstoppable.
So today I'm going to introduce you to the Anvil engine, or reintroduce you to this engine. Then I will dive into Assassin's Creed Shadows and some of its rendering pillars. And finally, I will talk about how we approach scalability and performances in this game and in the engine before concluding this talk. So let's start with Anvil. So Anvil was born with Assassin's Creed 1 in 2007, actually 2004 if you consider the development time. It's an engine designed for large systemic open worlds and long-range rendering, and systemic gameplay as well. So Anvil is mostly known for being used in Assassin's Creed, but it has also shipped many other big franchises, such as Ghost Recon, For Honor, and Rainbow Six Siege. And you probably wonder what a competitive FPS, a military shooter, and Assassin's Creed have in common. And me too. It's complicated. So over time at Ubisoft, we developed many variations or forks of the same engine. It all started with Scimitar, the Assassin's Creed engine. Then it forked into Blacksmith, mostly known for Rainbow Six Siege, and Silex, that is well known for Ghost Recon open worlds. So eventually we made several observations that would change the way we work at Ubisoft. We had so many engines at Ubisoft between Anvil, Snowdrop, Dunia, Voyager, UbiArt, and I'm probably forgetting many more. But we also had too many forks of each engine. Like you see there were 3 for Scimitar, the same amount for Dunia, and even more. And so it led to a multiplication of effort and developments, and we started realizing that big developments have a long life. It takes multiple years to develop big systems, and they can survive up to a decade in a code base. So we don't have many opportunities for full rewrite of big systems. And ultimately, we believe the multiplication of efforts made us less competitive. So working on the same feature or system in so many engines didn't make sense really anymore. So today, we work with Anvil as a shared engine across multiple games, genres, and brands. We work in a monorepo, one single code base, and our teams are scattered across the world between the tech teams and the production teams working all together. So now, let's dive into Assassin's Creed Shadows. So when we started working on Shadows, Valhalla had just shipped and was our benchmark for open-world AC RPGs. AC Shadows will be the first next-gen, truly next-gen Assassin's Creed game. So Valhalla was a cross-gen title with little scalability already. Its quality and performance modes had two very similar frames, and the main driving factor for scalability was its render resolution. As you can see on Xbox Series X in 4K native, we were only using like barely above 20 milliseconds of the GPU at 30 FPS. So looking at this, when we started working on Shadows, we knew we wanted to push the scalability to the next level. So what is the scope of Shadows? So it's made with Anvil, obviously. It's a 16 by 16 kilometers open world and has a time of day. So far so good, it's Valhalla. Then it has also massive destruction, ray tracing, virtualized geometry, and I'm not finished. It also has systemic weather and seasons. And I swear I don't work for this guy here, but when I saw this list at the start of the project, I probably made the same face. So it turns out it wasn't so crazy because we shipped it. And here you can see various dimensions of this complexity with time of day, systemic weather, and seasons with the winter. So in another view of the same thing with different time of day snapshots, some weather states, and finally the 4 seasons. So AC Shadows is a Gen 5 only title, as I said, and we have 3 modes on consoles between performance, balanced, and quality modes, with various target resolutions, as you can see here in this spreadsheet. We decided very early in the development that ray tracing would be favored in quality modes. So now let's dive into rendering. Anvil is built for long-range rendering from the ground up. The world is partitioned in cells, and the engine is built for multi-user editing in mind. The data itself is organized as streaming grid layers. We have several of these grids, and their definition is fully data-driven. So this is, as a large summary, how the grids are organized in AC Shadows. It could be different in any other game with our engine. In a nutshell, we have what we call LOD grids with the short-range main grid and long-range grid. And the difference between these is basically most of the assets will go to the main grid. Short-range will have mainly props that can disappear closer to the player because they don't really matter for the general rendering and gameplay. And the long-range rendering is mainly for big assets or point of interest that we want to retain for a longer distance. So loading grids can be specified at the entity level, and draw distances are driven by what we call LOD selectors. And they're constrained by loading grids, so you have to have them matching, otherwise you could have objects disappearing with the wrong setups. And so beyond the LOD grids, we have the fake entity grid that is that contains decimated assets and aggregated assets, so and can go up to 4 kilometers. And above that, we have what we call point clouds, that is our mass imposter rendering, and renders until 8 kilometers. And finally, above that, beyond 8 kilometers, you will only have the terrain vista with many details baked into it. So here you can see the naked terrain of Shadows with absolutely nothing. Then we have the LOD meshes, so the short, main, and long-range grid. And finally, the fake entities and point clouds. So in reverse order, we have the fake entities that are not supposed to be seen that close, then the corresponding LOD meshes. So I mentioned our point cloud renderer, that is a mass quad renderer that we use to render trees up to 8 kilometers away. This is without it. This is with it, so I will go back and forth because with the fading it can be hard to see, but it's really everywhere. and this is a debug view to show the amount of imposters we're under. It's really like a lightning fast quad renderer. So GPU-driven pipelines have been the cornerstone of Anvil since Assassin's Creed Unity in 2014. It shipped many games and went through multiple iterations. From left to right, Unity introduced GPU cluster culling and indirect draw calls. In the middle, Valhalla pushed this even further with mass instancing and batching. And finally, in Shadows, we added the support for virtualized geometry. So in AC Unity, the batch renderer, as we call it, was a DirectX 11 class API GPU-driven pipeline. I said it. The main goal of the batch renderer was to reduce the cost of expensive DirectX 11 draw calls. But it relied on multi-draw indirect for that, to call and render clustered meshes. And it introduced fine culling at the instance, cluster, and triangle level. So the batch renderer had still significant parts of it still on the CPU. It didn't support bindeless textures, which limited the amount of batching we could do. It was only really per material batching. And it also didn't support async compute, as you can see in this capture. So it had a significant cost and was delaying the render of the meshes. So the second version of our GPU pipeline is called the GPU Instance Renderer, or GPU-IR. It is designed for DirectX 12 class APIs. It is fully manless, and batching is now performed per shader instead of per material. And the GPU-IR performs batching at load time, and is designed to call millions of instances per frame. As you can see, many more steps were moved from the CPU to the GPU with this new pipeline. And to achieve that, the GPU-IR relies on something we call database. So I know what you are thinking. Where am I now talking about database? But it's not what you think. Database is a container for data structures that can be shared between the CPU and the GPU. It follows data-oriented design with a referencing mechanism. Think of it as a super structured buffer, really. We rely on shader input groups, or SIG as we call it, our internal compiler for shader bindings to generate all the helper functions and the binding code. So we augmented this SIG language to also declare tables. So in the context of the GPU-driven pipeline, database is used to share the full scene description between the CPU and the GPU. And we use database analogies, so it's where the name comes from, to structure our data. In this example, for example, a row myObject is just the equivalent of a pointer to a myObject. So this is an example of how we declare a table in our SIG format in the top, and how we access the same members in C++ and HLSL. All the interface, again, getters, setters are generated, so it's very easy to manipulate. You don't have to write that. One of the key features of database is the support of relations. Relations link different tables between each other. So one-to-one relation is the database equivalent of a pointer, really. While a one-to-n relation is an extension of this concept, and it simulates a pointer with a size, for example, to point to multiple children. And now you see where I'm going. We are going to be able to have a full C++-like description of mesh relations and properties. So different table instances handle CPU and GPU storage, and we support a different mode of data replication to ensure that the data is propagated from one instance to another. And it's generally from CPU to GPU, but you can do more than that. So we have the copy mode that is the most simple one, and we'll copy the whole data from the CPU to the GPU into a byte address buffer. Then we have a dirty row and dirty pages update, and this maintains a dirty mask at the row or the page level, and replicates dirty rows or dirty pages, following what you decided to do, to the destination table. And finally, for very large tables that we don't want to store fully on the CPU because it would saturate the memory, we have a mode where we only store dirty rows on the CPU until they are flushed out to the GPU. So this is what our scene description looks like on the GPU, and it's quite close to the CPU representation. It's not identical because we don't need exactly the same parameters, so we optimize it. But you see, it could be the same. We could have a similar thing on the CPU. In a nutshell, CalMesh has up to 5 loads, And each load has two LOD distances, one for the main view and one for shadows, to allow customization for shadow LOD distances. And the association of a geometry with a PSO is made at the submesh level with a batch hash, as we call it. And we make sure we only have one batch per PSO, so there are absolutely zero duplicates. And this is how we declare all that with tables in SIG. So it really looks like structured buffers, really. And each table are linked by row and range relations. So if we zoom out even more, you see the previous slide is in a little square at the bottom right. Now we want to focus on leaf nodes and curl instances here. So we also see the world is organized as a quad tree. And to achieve good culling performances, it relies on a hierarchical structure made of entity groups and leaf nodes. And leaf nodes really is a group of instances, and probably we should rename it in the engine. So we gather instances that are spatially close to each other in the same leaf node to minimize their bonding volumes and to make coarse culling more efficient, because this step is done on the CPU. In terms of code, this is roughly the life cycle of tables. So first, we declare CPU tables and GPU tables separately. Then we populate tables. In this case, we create a mesh entry in the curl mesh table, and we set various properties to this mesh entry. Then eventually, we will trigger an update of these tables to the GPU. So I don't show the underlying code behind that, but it's an implementation of the replication policies I described before. And finally, on the GPU, we fetch this data and use it as we like. So the interface is very C++-like, but it also maintains maximum cache efficiency in data access patterns, because we can use annotations with this language to decide if a table is a structure of arrays or of structures, and even do mix and match. So really, database is a sort of super structured buffer that I would like to have in DirectX. So finally, this is what the entire GPU instance renderer pipeline looks like. And I will redirect you to the GPU Zen 3 articles if you want to have all the details about that, but I will still describe the most important ones. Because there are some steps that are very specific to our engines anyways, like maintenance code. So on the CPU, there is a coarse Frustum culling to cull leaf nodes, basically a group of instances, as I described. And on the GPU, if you look at the two next columns, there is frame culling and per pass culling. So the frame culling cull instances that pass the CPU culling against all the view frustrums of all passes. And then LOD selection and blending logic is also performed at this stage. The per pass culling performs pass-specific frustrum and occlusion culling. And for example, for sun shadows, we do anti-frustrum culling per cascade. It also prepares instance data that is required by the vertex shader and pixel shader to access geometry and material data for a given instance, because we work with unified buffers and for vertices and also for materials and constants. So we need to maintain a form of description of all that to know where to access the data. And finally, at render time, we support optional cluster and triangle culling before the final executing direct call. So additionally to the GPU instance renderer, we added support for a micro-polygon geometry pipeline. It's based on the Night from Brian Caris. It was presented in 21. In this pipe, it's an evolution of discrete clustered mesh pipelines, really. And in this pipeline, a mesh is made of a cluster hierarchy with continuous level of details. So we stream clusters individually based on their visibility, and polygons are either hardware or software rasterized based on their size. So micropoly is used for gbuffer and shadow rasterization. And in this pipeline, geometry takes roughly half the memory of the same geometry in GPU-IR. It shares similarities with other techniques. For example, we use the same Metis library to perform cluster partitioning. We either use mesh shaders or software rasterization depending on the triangle size. It also has two-pass hierarchical Z-buffer occlusion system. It renders different materials from a VZT buffer to a G-buffer. And also clusters are made of 128 triangles, as opposed to 64 triangles for older GPU-driven pipelines such as AC Unity. So some differences though. in our case, for mesh simplification, we still rely on Simplygon to generate the cluster group simplification. It does a good job at that. We support user custom code shader with a manual API to allow for custom shader code in the shader graph. Our pipeline is also fully bindless as it is with the GPU instance renderer. And during software rasterization, one thing we did as well is to swap X and Y coordinates depending on the triangle configuration. So basically, if it's horizontal or vertical, to improve branch coherency, because this algorithm basically performs scanlines algorithm to rasterize the triangle in software, and usually it's performed horizontally. But if you end up with a vertical triangle, flipping it will improve branch coherency and workload balancing. So some stats. We currently only support micropolygon for static opaque geometry. And in this game, it's really the main city architecture and static geometry renderer. And GPU instance renderer on the other side is our massive alpha-tested vegetation renderer. So in Kyoto, we have around 28,000 micropolygon instances for 34 million triangles rendered. And as you can see, in this precise case, 90% of the triangles are software rasterized. But this, of course, depends on your geometry tessellation level and also the render resolution. That will change the coverage of pixels you can have per polygon. For the GPU instance renderer in this scene, it's mostly trees, and we have around 9,000 instances spread across all passes for close to 2 million triangles with it. So the reverse scenario now in a forest. Micropolygon is less solicited in this scene, as you can imagine, but it still renders some buildings and rocks here and there. I'm actually standing on a building here. And it's really the GPU instance renderer doing the heavy lifting in this forest. So we call 3 million instances to finally render 30,000 of them. And the scene before culling has 1.5 billion triangles, and we end up rendering 7 million of them. So really, we had no pressure to support alpha test with a micropolygon, even if it's definitely something we are going to do in the future. So now let's dive into my favorite topic, global illumination. It's always been a first-class citizen in Assassin's Creed games, and also in my heart. In AC Unity on the left, we developed a volumetric open-world GI. In AC Origins in the middle, we made it sparse to adapt it to very large open worlds, like 16 by 16 kilometers open world. And finally, in Shadows, we added support for seasons, and we also developed a new ray-traced global illumination pipeline. So for Shadows, we targeted a scalable GI pipeline from the beginning. We know ray tracing is costly, and we didn't want to sacrifice other parts of the game to ship it at all cost, especially at 60 FPS. And moreover, considering the hardware landscape, it made sense to give more choice to the players, and we can see it's generally well received to give this choice. Our GI pipeline is more of a spectrum going from fully baked diffuse and specular to ray-traced diffuse and specular again. So ray tracing can be either rendered in hardware and software with compute shaders. And there is one special case in this game. We have the Hideout, that is a fully dynamic kind of SimCity construction, and it requires ray tracing, otherwise it will have no GI. So the first version of our baked volumetric GI dates from AC Unity. It was baked on a GPU using ray bundles, and I will refer you to the great talk of Josh Hobson about indirect lighting in God of War. And it's based on the work done in ACU, and it describes very well the pipeline. The main difference with Unity is the open world structure. So the system went through multiple iterations. For example, we didn't support time of day at first. It was added later in the next game, Syndicate. So in AC Unity, the world was covered with a uniform mip-mapped irradiance volumes, and mip-maps acted as a level of detail at farther distances. It didn't support dynamic time of day, as I said, and it was faked with 4 fixed static ambiances. Later, Syndicate added dynamic time of day by blending between 2 fixed GI keyframes. So as you probably know, Assassin's Creed pivoted to more RPG-like experiences with larger open-world games since Origins. And if we naively extrapolate numbers from Unity or Syndicate, we see that the baked GI technique would never have scaled to 16 by 16 open-world games. and you can see it would have made up to 500 gigs. If we push this even further, Shadows adds 4 seasons, and now we are close to 2 terabytes of GI and over 600 days of bake time. And even if we consider we have an infinite computing farm, which we could have today with Google, Microsoft Cloud and everything, we still have to make the space on the Blu-ray for this, so we had to do something about it. So the first thing we did was to shift to a CPU path tracer backend, and for several reasons. The GPU baking requires a lot of VRAM, and memory cliff was a real issue, especially at the time of Origins. There are also less variations due to drivers and diverse GPUs on the build farms. And it makes our inputs deterministic, so we can know exactly what to bake and what not to bake. And so it's faster to dispatch because less work is performed on the local machine. And we also introduce the concept of a density map and sparse probe placement. So in baked GI solutions, texel and probe density is everything. It's really where the details come from. But it doesn't need to be uniform across the whole world, and this is the key to saving space. So we use a density map to paint the GI resolutions to ensure we have the right amount of details where it matters the most. And with this, only a fraction of the map is at the resolution of older games such as Unity. AC Unity had 50 centimeters voxels everywhere in the world, whereas in this map you can see it's only the blue areas, many cities, that are at this resolution. But these areas are still larger than the areas of those games, previous games, so data is still too big. So what can we do to address this? So to further decrease the size of the baked GI, we distribute probes in a sparse octree. And a node is subdivided only if it contains surface. We also discard probes that are inside geometry to save even more space. And in average, we end up with roughly 10% of the probes we would have with a uniform distribution. So to support time of day, we store 11 keyframes, 1 for local lights and 10 for different positions of the sun. As I said, it's fully data-driven, so you could imagine you have more for your needs. We store the sun, local lights, and sky separately in a YCOCG format. And so the luma value is, the Y value basically is directional and stored as spherical harmonics, while the chroma values are scalar. And for seasons, we aimed at a minimal bake size overhead, even though we have to bake the GI multiple times. So we made 2 assumptions that we know are fundamentally wrong. First, spring and summer would be the same season as far as indirect lighting is concerned. And to be honest, it's not such an approximation because the albedos are almost identical, if not identical. And the variation of these seasons comes more from asset changes and fog and weather. And second, the luma remains the same for all seasons and is stored only once, while we store separate chroma values per season. And it's clearly an approximation. If you want to break it, you can break it, because there can be mismatch between luma and chroma values. For example, if a geometry changes between seasons or doesn't exist in each season. But in practice, many vegetation is heavily affected by seasons, and problematic geometries can be flagged out and skipped in the bakes. So a tech artist can just remove problematic objects. In practice, we didn't have many problems. So at runtime, sparse voxels are inserted in cascaded 3D volumes. So those cascades are uniform. We sample uniform cascades at runtime. So it goes through a decompression step to make the sparse data not sparse, and then it is inserted in the cascades. So we perform cross-cascade blending and in-place GI block LOD blending when the block is loaded to avoid popping with new LODs. So on the left, we had a discrete GI grid of GI block, as you can see in AC Unity. And the mipmaps or load stream with the view distance, so in a discrete fashion. Exactly as we do for distance-based 2D structure streaming. It's exactly the same thing, but with 3D volumes. And it worked well, honestly, the game was beautiful. On the right, it's the sparse GI blocks that are inserted in a cascaded GI volumes to create a much more continuous level of detail. So for some numbers, here in the back you can see various stages of the bake for AC Shadows, with top left the voxels, Bottom left shows the cascade grids density at runtime, and the final lighting at the bottom right. So as I said, if we had followed an approach similar to Assassin's Creed Unity, we would have ended up with 2 terabytes of GI data, so it would really have blown up the space. But in the end, we end up with roughly 9 gigs, mainly relying on the density map and the sparse grid. So for some results, as you can see, we didn't go for full exactitude or accuracy. It's clearly an approximation. But in the end, it gives plausible and believable results. And we are pretty happy with it, considering the size. So for specular reflections, we use in the following order screen space reflections, relatable gbuffer cube maps, and a dynamic cube map at the player position to act as a regional cube map, as a fallback. So gbuffer cube maps are not something new. We provide albedo, normal, depth, and they are dynamically relit at runtime. Shadows are also baked in these cube maps, and to do so, we store 8 keyframes in an 8-bit texture, 1 bit per key. And then at runtime, we select 2 keyframes closest to the current time of day, and we blend them accordingly. And it works very well. It's surprising. It's a nice trick. And really, because the cube map's resolution is not so high, you don't even see there is no filtering. For seasons, we use what we call variation states. And variation states allow for data-driven game-specific logic at the entity level, and we use it mainly for seasons. In practice, we store 3 variations per cube map, and I will remind you, spring and summer are considered the same for indirect lighting. And in total, we have 16,000 cube maps in the game, so it's silly. And I'm not counting the variations. So not all of them have variations. There are some interiors where we can skip having, for example, a winter variation, but most do. Our dynamic cube map is written to be very, very cheap to render. It renders fake entities, so basically decimated, aggregated level of details. And it uses the lower resolution far shadows. And as you can see, a comparison on the left with the dynamic cube map, on the right is the same local cube map, the same position. And they are pretty close. So finally, just to show some variations of some local cube maps to see how wide the spectrum of what we can render with it is. So now, as I said in the beginning, we also support ray tracing. It was a big development in our game. And we're particularly inspired by the work done by the Snowdrop folks at Ubisoft. And we decided to follow a similar design favoring inline ray tracing and supporting both hardware and software ray tracing. But we were lacking data to back this up, and we weren't sure if it would fly or not. So we wanted to keep our options open, and for this we went for a complete abstraction of inline, non-inline software and hardware ray tracing. So our ray tracing stack is abstracted under a hardware abstraction layer that we call Fusion, that is shared at Ubisoft across multiple engines, and it's developed following an insourcing model. So this library is basically in our internal GitLab, and following the insourcing model, we can contribute and make it better for many projects at Ubisoft. So we developed a unified ray tracing API to abstract platform-specific APIs, which is fairly common, I think, but also hardware and software ray tracing, probably less common, and inline and non-inline. So we wanted switching back and forth to require minimal effort. And so on the right, in the green square, you can see our ray tracing loop with a callback interface. And in more details, this callback interface serves as an inline and non-inline abstraction. When using inline ray tracing, depending on the required state, it will invoke the corresponding callback, so hit, any hit, miss. And so it's the responsibility of the user code to write these callbacks as if they acted as the different shader stages we get in the non-inline ray tracing code. So in the case of non-inline, you can do the same thing. You can just call the same callback in the corresponding shader stage. So for example, in the miss shader, you will just call the same function and so on. But of course, for each shaders, you probably want to use shader tables, otherwise you wouldn't be using non-inline. But for us, we think it's very practical in practice because switching back and forth between the two pipelines can help validating assumptions, testing new functionalities, and seeing what works best for your game. In terms of C++ code, switching between software and hardware is super easy, simply done with Nenium, and actually we even support CPU ray tracing the same way on some platforms. And the difference to set up inline and non-inline ray tracing is also minimal. I show in the bottom some code, probably will read it at home. It mainly comes to setting up the shader table, really. So our hybrid ray tracing GI combines two steps. First, there is a per pixel ray tracing made of screen space rays and world space rays, and a DDGI-like probe cascades made of 5 cascades for a total of 10,000 probes, and we update 1,000 probes per frame, more or less. So our ray tracing hits are stored as a set of PBR properties in a ray tracing gbuffer, and then we write the hits in a deferred lighting path. So this is what our ray tracing pipeline looks like. So we first trace secondary rays in a screen space, and this acts as an acceleration because everybody knows hardware rays are very expensive. So we want to avoid using them if you can, without any approximation, resolve them in a screen space. So if we find a hit, we store it in a hit buffer, and if we don't, we keep this ray with the same t-value, and we fall back to world space ray tracing, that is basically tracing with hardware rays the BVH. So continuing the t-value and continuing stepping in a world. So all those hits end up in a hit buffer, then we relight in a hit lighting path in deferred. And if there is no hit for the given pixel, then we'll trigger a miss event and sample a probe cache. So this gives us the first bounce, basically. And to get the subsequent bounce, we sample the DDGI cascade to bring back the rest. So then everything is denoised, and we can add an optional RT-AO term, as I called it, that is artistic driven, and RT-specular if it's available to produce the final image. So you will ask me, why do we add AO at the end? Because it's supposed to be part of the light integration, right? So there are multiple good reasons for that. First, we sum two systems with different frequencies, with per pixel rays, but also with ray trace probes. And so ray trace probes can attenuate some details, especially in AO. We also trace rays at quarter resolution in screen space on most platforms to help performances, so we can lose high frequency details. And finally, there can be some disparities between the raster world and the ray tracing world. For example, we don't have the grass in the ray tracing world, because again, for perf reasons. So if we reapply some RTO at the end, you can see, I go back and forth, it helps a lot the large objects like houses, trees, and so on, to ground them to the frame. And we also still evaluate a very subtle SSO term to make up for the fact that we trace in quarter rays and bring back like centimeter level details. And you can see, when I add this term, it helps a lot the ground and the leaves and so on. So this is the final image. So our acceleration structure works as follows. We support both bindless textures or average color for metal textures, for example, for very low-end platforms. We call meshes by size or type, and we use a global LOD offset to determine what to put in a BVH. And for micropoly, we base the section on a LOD error metric to output proxy meshes, as was mentioned by NVIDIA yesterday for these techniques. It's the best way to do it currently without mega geometry or these kind of things. So, of course, everything can be overridden per asset or per material to address local issues or if you want more details locally. So this is an example of our acceleration structure with, at the top right, what we shipped in shadows with bindless textures, and the bottom right, the gbuffer albedo for comparison. So for alpha test, we tried several things. We tried using the blue noise approach to approximate a transparency factor and stochastically text kill the right amount of texels. Then later we added bindless alpha texture support. With close to no overhead, everything was already available because of our GPU pipeline. But we ended up with either one of these two issues. So if we want a precise result, any hit is very costly with many overlaps. So it's a bit of a deal breaker in the kind of forests we have in the game that are silly. And if you try to limit the number of hits, then you end up with way too much occlusion. And we even tried things like trying to compensate for that only in the vegetation, but we are not satisfied. It's more of a hack. So in the end, we set up for another way that we think is a bit, we didn't believe in it, but we tried it and it worked very well. So basically, we scale triangles according to their average opacity, as you can see in the bottom right image. And in practice, it's 30% faster to trace than any hit. And the diffuse GI looks actually quite close to the reference. And it works very well in practice because closest hits are resolved in screen space, and this is really accurate. So you get the best of two worlds, pixel perfect result for screen space, and you have all the layer of translucency at the same time. And as a bonus, it's a very good approximation for specular ray tracing as well, even though you are rendering disconnected sets of triangles for leaves. So because we use inline ray tracing, we rely on the Uber shader approach for ray trace materials. And to be honest, I panicked a bit when I watched the Capcom talk about remapping shaders with JSON files. So I was really hoping we wouldn't have to do that, and we didn't, because at Ubisoft we are very strict with the shader variety and management. We have a low master shader count, and it's mainly for GPU-driven pipeline reasons. We want to reduce the number of executing direct we have to do in a frame. So in the end, it was relatively easy to write a one-fits-them-all Uber shader. But of course, there were some epic fails. There always are. And but as I said, it can be easily mitigated with overrides. We can override anything in the BVH, LOD meshes, material attribute, shaders, everything. So as I said before, we use a unified representation of materials. They are stored inside a material table that we access with the hit geometry ID at hit time. And seasons are handled with a material variation in this table to account for fallen leaves, to not create too much occlusion, and also the use of lookup tables for leaf colors. Deferred weather is fully evaluated for specular ray tracing, but not for diffuse because it'd be too costly to evaluate it multiple times. And it's probably something we are going to solve in the future. Static snow is baked in the Terrain Vista though, so it's still accessible for diffuse. And this is what our acceleration structure looks like for each season in the same scene. So in a typical urban scene, this is an Xbox Series X, we end up with roughly 2,000 blasts for 30,000 instances and a total of BVH data of 320 megs. It's bigger on PC, of course, because there are more things at play with hardware abstraction. Our software ray tracing stack is very similar to Snowdrop's. It's part of our low-level abstraction, Fusion. It is mainly aimed at lower-end platforms, so it's not something we shipped on consoles, for example. It's more like for very low-end PCs, like 1070s and so on. So it's structured as a 3-level BVH that we also abstracted in our low-level API, and relying on space partition to perform partial updates only when something has been loaded in a cell or an object is moving. So we still rely on indoor volumes to avoid leak in interiors. And they are made of a list of planes, and it's the same data we use for baked GI, but also for many other systems, such as deferred weather, but even sound. And they are used to classify probes. So at sample time, at the sample position, we find the 8 surrounding probes, and then we sample weighted probes with the same classification. Our light probes are convoluted into an irradiance cache, pretty much as a DDGI from a Maguire, and also as a radiance cache that acts as a fallback. And to stabilize the signal, we trace shorter rays and fall back to the radiance cache, which is temporally stable. And as you can see in the video, before and after, in a very challenging scene, because it's mainly indirectly lit and the openings are very narrow, actually, the result with and without it is pretty telling. So the output is a bit less precise, and it's clearly a trade-off between pixel-perfect precision and stability. So for translucency, we stochastically flip rays on translucent surfaces, and also if a secondary ray hits a translucent surface, such as a Soji door, so a Soji door is a Japanese paper door, we sample probes on both sides of the surface and blend accordingly using the translucency factor. So local lights are inserted in what we call an omnidirectional clustered lighting structure. It's based on a regular cluster lighting code, so something that is usually in every modern engine. And the main difference is that the clustered volume is mapped on a uniform grid around the camera. So you can see in this video the difference between frog cells here and the omnidirectional structure that comes after. So the difference is in this structure, we have a two-level hierarchy. We have I clusters and clusters. And I clusters contain 16 by 16 by 16 clusters for a total of 260K clusters. And we first perform a coarse cluster culling and then a finer grain culling at the cluster level. So as discussed mainly ray trace diffuse, but we also support specular ray tracing. It was really a last-minute effort at the end of the game after it was delayed. So it's a bit crazy. We managed to ship it, honestly. It follows roughly the same design as Ray Trace Diffuse GI. We mainly target high-end platforms with it, so PS5 Pro and PC. It was a relatively easy development, honestly, leveraging most of the work we'd done for Diffuse, and we suffered to get it right. And we had to run mainly BVH quality issues that were not really noticeable with low-frequency Diffuse GI, but also denoising. So for denoiser, speaking of denoising, we have 3 of them in the engine. We have a true denoiser that is similar to SVGF family class of algorithm. We also have NRD reblur from NVIDIA, and we have MSD from Soundrop, and this is what we shipped. So it is a spatial and temporal filter based on a recurrent blur approach, exactly like reblur. But what we do, we also support a material masking for characters, vegetations, and dynamic objects for specific heuristics to handle disocclusion challenges and so on. And we also support spherical harmonics denoising. And for this, we store the signal in the Y COCG with Y being a spherical harmonics. So this is the raw output we get from Ray Trace Diffuse. This is after denoising. And this is with spherical harmonics denoising. So I'll go back and forth to show you how much of a difference it makes. Final lighting and the final image. So this is with baked GI, an interior scene. It's not too bad. This is with Ray Trace Diffuse. And this is with Ray Trace Specular on top. So I will go back and forth. Even though the scene is not very reflective, you can see Ray Trace Specular helps grounding the whole image. So this is an outdoor with just Ray Trace Diffuse, and now with Ray Trace Specular. And you can see everything that is out of Ostrom is still reflected properly. So for performances, what are the cost of our Ray Trace probes? So basically, it's 1 millisecond on most consoles, except of Pro, PS5 Pro that has a better ray tracing performances and hardware. And for per pixel ray tracing, we're roughly around 4 and 5 milliseconds, again, except the Pro. So we arrive at a total of between 5 and 6 milliseconds for diffuse. That is spread across the graphics queue and the async queue. For Specular, it's another story. It's quite expensive, and the main reason for that is because we shipped it at half resolution, so half divided by 2, but full height. And the idea was to ship it in half res because it looked significantly better, and we had the budget for it. We still managed to maintain our target resolution on a PS5 Pro because everything was a bit cheaper, and also we divided the cost of diffuse ray tracing significantly. So now about weather and seasons. We adopt a systemic approach for weather and seasons with Atmos as a fluid simulation and an ambience graph. Our rain and snow are rendered in deferred, and we also introduce the concept of multi-state entities that I mentioned before. So Atmos would deserve a whole talk by itself. It simulates and propagates atmospheric factors with a fluid simulation, such as vapor, temperature, humidity, and it collides the wind using low-resolution voxel data at runtime around the player. These quantities are fed to various systems, such as volumetric clouds, to drive their formation and dissipation, but also wind and rain. And on the right, you can see some quantities that we simulate a function of the altitude. So in previous games, we relied mainly on an ambience manager system, and we used it to drive time of day, lighting features, post effects, and so on. It's mostly made of curves and has limited logic. But for shadows, we developed an ambience graph system that is based on our node graph system and fully data-driven. The ambience graph will consume inputs from the engine, from Atmos, and drive the whole weather incident stack logic. And it's really like TechArt-driven. The TechArt can decide how it wants everything to behave. So our deferred rain rendering is based on Sébastien Lagarde's great blog post series. It's very well known. We used to maintain and render wetness and puddle level by darkening albedos and decreasing roughness based on wetness levels. So this is an illustration of how it works. In the first row, you have the final render function of the wetness and puddles. In the middle is the wetness mask that we store in a gbuffer. It's a single float. And in red is the things, many characters that are not handled by this system because the characters have a dynamic character layer system for this. So this is a step-by-step with the dry scene, then the wet scene, and then with the puddles. So also snow is an important part of our game. And for this, we have first what we call deep snow. It relies on a data-driven stamper that we can stamp captures and textures. And we can use it to deform the terrain or any height map. Also, next we have deferred snow with a dynamic accumulation. And it's like a deferred rain, really. It works the same way and modifies material inputs. And we have the concept of cold and warm zones driven by a static dynamic snow mask painted by a tech artist. So as I said before, the deferred snow modifies the material inputs. So it layers albedos toward the snow albedo, and generally it's white, according to the current snow level. It does the same for roughness. And it also lowers translucencies, mainly for vegetation, the higher the snow level is. Then we mask it out with micro visibility. And finally, you threshold it with snow based on normal orientation to simulate the fact that the snow doesn't accumulate on vertical surfaces. So this is the whole sequence of dynamic snow accumulation. What I don't show here is that when the snowstorm dissipates, the snow will slowly decay, the reverse of what's happening here, and then turn into wetness and puddles, and to finally melt and dry. And the logic is really driven by the ambience graph. It's doing everything there. So to exclude deferred snow and rain from interiors, we use the same indoor volumes again from BakeGI and RayTraceGI and so on. We rasterize them in an indoor depth map, and we use it to determine the occlusion factor when we apply the weather. It's very cheap to render this indoor depth map. It's just planes, basically. For particles, we render the surrounding in a depth map oriented with the rain direction. And we use it to occlude rain particles and rivers. So basically, the rain particles can penetrate through a window in interiors. So now we'll talk about how we approach scalability and performances. So mainly due to the fact that we ship different GI systems in performance and quality, our frame looks very different from in either mode. So to manage all that, we developed what we call the platform manager, and it's how we implement data-driven performance settings per platform and context. It's mostly, but not only used for engine and graphic systems, and the UI is auto-generated and everything is live editable. So profiles are basically performance mode, quality modes, and so on. Profile settings require reloading the world, while profile boot settings require relaunching the executable. And you can see some examples on the right. So AirStrand memory budget. So there is GI technique, but actually because it's a bit special in this game with the hideout, it does not require restarting the game or reloading the world. Context is triggered by gameplay and can be, for example, when you go to menus or photo mode or go back to the game world. And it's a way to fine-tune render features and performances for specific scenarios. You might want in photo mode to crank up your hair rendering, for example. Modifiers are triggered by data, and they can be painted or triggered by 3D volumes. And it's mainly to address localized performance issues or specific needs. Imagine you are in a cavern, it's very different from an open world, so you can maybe even disable some render systems. So to summarize, the Platform Manager is a first-class citizen in Anvil. It's great for fast iteration and profiling, and it's very useful to iterate with vendors according to them, so I trust them. We can simulate console settings in the editor, even though it's a bit limited. You cannot really anticipate what you will get, but you get the idea. So to track translate resources, we use two internal tools. We have a high-level view available to track resource lifetime and also find the memory peak in the frame. And we also have a low-level tool to inspect our allocators and debug, for example, memory waste or memory aliasing patterns that might be undesired. We also have a lot of telemetry in the game to track performance regression. And all these counters are stored in a database and everything. So there are a few examples to track, for example, dynamic resolution factor at the bottom right, given in every position possible in the world, compared to builds on PS5 to track GPU regression on the top right, and so on. So to conclude, AC Shadows is really is the first game we shipped with a monorepo and a shared engine. It's the largest AC game we've ever made and uses the most scalable version of Anvil to date. So what would we improve? So we developed a lot of technology in this game, and we had to anticipate many things like poly budget and everything to avoid, we had to be a bit conservative to avoid having to rework all the assets in the end because we made a huge mistake. But in the future, we really want to use MicroPolygon even more, support it in more pipelines, and increase geometric details. Baked GI and Retrous GI is hard. It's really hard. It's good for players, but it's really difficult for developers. And so we really want to make ray tracing more prevalent to simplify our life on our pipelines. But we think giving trust to players is always good. And the game was insanely hard to QA with all these different time of day, seasons, and so on. And so the upscaler, the upscaler world is very fragmented and makes everything even more complicated. So yeah, I wish we could do something a bit simpler here in the industry. But I think it's time to rethink how we approach this complexity in general, QA, and also how we present it to the player. And finally, graph-based seasons and weather made it very easy to prototype and find the right recipe for the game. But again, difficult to QA and repro issues. And we think it's an idea that requires more iteration and maturity. But we definitely want to push frame modularization and customization further, especially in the context of a monorepo and a shared engine. So for some bibliography. And I will be taking some questions if we still have time.
Great talk. And
thank you.
Hello. I saw that recently you also launched for the macOS and iOS platforms.
Yeah.
How different was to work on those compared to PCs and consoles? And basically, what tier would you assign those devices?
The scale of platforms is very large between M1 and M4. And low-end platforms were a bit of a challenge, but we managed to run it by really compromising things that are not necessarily things that will break the game on those platforms. I think the main challenge was working on a Mac environment, having to work directly in Xcode and these kind of things. It's always, we are used to Visual Studio. Also, it helped. We had software ray tracing, because I think it's what we shipped on the lower-end Mac, but I would have to check to be sure. Because with I spoke about the Platform Manager, it's so dynamic that sometimes you lose track on what you ship on what platform. But I think it's what we used for lower-end Macs.
Thank you.
Thank you.
Hi, great talk.
Thank you.
I would like to ask, I think for Nanite, this challenge is that the foliage is quite hard to compress. And
for Nanite?
Yeah.
Yeah.
For the cheese.
Yeah.
Did you have any optimization to use micropolygon for cheese?
Actually, as I said, we don't support alpha test at the moment. And really, the main idea behind that is that we don't have any pressure to do it because we have a super efficient GPU-driven pipeline for alpha test. And as you can see, it renders millions of triangles with no problem. You see the forest we have. So we're like, okay, we're going to focus on opaque geometry, get it right, and after we'll work on alpha test. So, but we know it's a challenge, and we want to take time to get it right. Yeah.
Cool. And my second question is that you have to support many platforms like 33 milliseconds and 16 milliseconds.
Yeah.
Do you have a plan for the frame time budget or just optimize as it?
Honestly, the main issue was the difference between frames that didn't have RTGI versus frames that had RTGI. So performance mode and quality mode are two different frames. And so we tried to keep GPU scheduling as close as possible to avoid very specific bugs in each mode. It was a headache, honestly, and I think probably we won't escape to having tailored scheduling per modes unless we try to bring back those frames closer. Yeah. And there is also the challenge to work in a mono repo, so there are different games in the same code base. So anyways, we are going to need more customization for this. And we started having like data-driven frame graph scheduling and these kind of things, but we were a bit scared to push it a lot for this game.
Cool, thank you.
Okay, if that's all, thank you.